you have two wells in this anticline structure. In well 2, you have the well is penetrating only your aquifer and the oil column, right? So if you would like to, do the initialization by equilibration, then you have your datum and you have your composition, all right, which is the composition from the PVD. But you are not able to see the GOC. So in those three parameters which are needed for the equilibration, the GOC is high uncertain compared to the other two, all right? And if you look at well 1, you have the well is penetrating the gas cap and penetrating all the way to the aquifer. So what we have here, you have the datum, you have the gas oil contact, and here you may have to adjust the composition so to make sure all those parameters consistent. Consistency means the pressure that we get from the gradient supposed to the gas oil contact supposed to be equivalent to our saturation pressure. Okay, most of the simulators of today, can give you a facility to adjust the composition based on the other two parameters, which are the datum as well as your gas oil contact. But with the intersect, in the intersect, you have a flexibility. I mean, you impute all these three parameters, and you will be able to adjust any of the other parameters based on whether if it's high uncertain or not. Okay, so for model stability, the user supply the parameters such as the pressure, contacts, and the fluid composition. And the pressure, the gas oil contact should be consistent with the saturation pressure, as we mentioned before. Okay. Sometimes it may not be consistent. That's why you have to adjust one of those parameters to be able to be consistent. Intersect have a flexibility. Like for equilibration, you can impute your datum plus the GOC and possibly modify the composition. And this is what all the simulators are doing. I mean, and there will be sometimes one of those parameters is uncertain. You can provide the datum plus the composition, and you possibly move the contact allow the simulator move for you the contact based on the calculation from the other two parameters. Same as for once you provide the GOC plus the composition and want to ignore your datum pressure and depth. Yeah. Can you go? Yeah, come from the beginning. Yeah. In this is a demo, and in this demo, I would like to show you, how you will be able to, do the initialization by using the different methodology within Petrel. So first of all, you will be able to do specify your initial condition through the fluid model process. And in that one, either you have you input it manually, or you have your defined contacts, which you can use the contact set and drop it here, and you will be able to do your initialization. This is by using the fluid model process. The other one is by using the initial condition. Okay, and in the initial condition, it gives you flexibility of different simulators. You can see here you have Eclipse 100, 300, front sim, and intersect. In all of those four simulators, I would like to show you the differences of whether you have intersect or the other simulators. So we are trying to create now a new initial condition, and this new initial condition is whereby we want to adjust the gas oil contact. All right. So we drop the fluid model into the fluid model box here. That's what we are going to see. Okay, and then from there we specify our parameters. Like here we have the datum plus its depths, the datum pressure and the datum depths. Okay, All right. And then according to that, we just want to show you the difference whereby if you have intersect versus the other simulators, I mean, at least in the initialization, by using the initial condition here, you'll be able to adjust the other two parameters, you know, not just only the composition. All right. So this is just a demo to show that. Okay.
Oh, yeah.
All right.
Good afternoon.
Where is this?
Okay.
Hi, Samuel. Sorry.
Mokazo, do you want to ask a question?
Yes, indeed, I do want to ask a question. Thank you.
Yeah. So go ahead.
On the previous process where you were in terms of the setting the initial conditions.
Yeah.
And I see that, for example, on setting the initial condition, you had available places in which to put the saturation pressure and the RS value. But this is only in cases where you have oil water contact and gas oil contact, right? When you have both contacts.
Yeah. So if you don't, yeah, go ahead.
But now, if you, for example, let's say you're looking at a case in which you did not have like an undersaturated reservoir or saturated one, where you only have the oil water contact and you don't have the gas oil contact.
Yeah. So in that case,
initialization wouldn't be the same.
Yeah, it won't be the same. In that case, if you look at the process that is shown, that process actually gives you the option to choose whether you have whether you have gas oil contact or whether you don't have gas oil contact. That is when you use the initial condition process to set it up. So if you're using that to set it up, you have the option to indicate right away whether you have gas oil contact or whether you don't have gas oil contact. So if you choose the option that there is no gas oil contact, automatically you are defaulting to the undersaturated reservoir scenario. But if you indicate that you have gas oil contact, then it will pop up for you to enter the value of the gas oil contact. Even though you are indicating that you have gas oil contact, you can still go ahead to say, but it is uncertain. I'm not sure whether it should be placed on the structure because I'm not sure if I'm seeing it, or whether it should be calculated by the tool, by the software itself. That is also possible. And that is why those three parameters that Edwin was talking about in his presentation, they are very important to the initialization of the module, because you are providing the datum, you are providing the, let's say, the GOC, and you are providing RS. Providing two of them, the simulator can actually calculate the last one to ensure that they are consistent, because the pressure calculated from the datum the gas oil contact must be the saturation pressure. But coming back to your question, I'm just saying that we have different flexibility on that process to specify either for the saturated reservoir or the undersaturated reservoir. So you can do both. But let's say you are not using that process. You can still also put your GOC. Let's say you are using the first process, that is through make fluid module process. If you're using that, because you have to provide, there is a field, you cannot disable that on that process. GOC is there and OWC is there. So you can set GOC to be above the structure to indicate that you have undersaturated reservoir. So you can put a depth that is above the structure. That will make it undersaturated as well. That's another way to go about it.
Okay, I guess we'll be able. I will be able to see more of this when we come to the demo part, or still can interact from here.
Oh, sure, definitely.
All right. So I will wait for. I will just proceed. I will be able to raise my hand in case any questions pop in.
Definitely, that would be great. Thank you so much for that. So just to let everybody know, after this, once we finish with the conventional initialization that my colleague is explaining, we're going to be looking at some other workflows that are connected with the SCAR section that we had last week. So how do you move from generating the water saturation array to initializing the module? Then we'll look at some of these concepts towards the end of this presentation. Sorry, Edwin, for the interruption. You can just continue from there.
Okay, that's fine. I think since we already highlighted about the two process of doing the initialization.
Yeah.
All right. Yeah. So as we all know, like with the equilibration, this is what the process happen is like you have above the transition zone. You usually like above the the transition zone, you have the connect water saturation, and then you calculate the saturation of the cells according to the equation of 1 minus SW. Same for gas, like within, if you have a gas zone as well, you will do the same calculation, and below the free water level, you have 100% water. But in the transition zone, what you do is you do the phase pressure calculation and do the the non-wetting phase minus wetting phase to at least get your capillary pressures, and then from there, since you have your saturation function table defined for your simulator, you will be able to reversely look up at it to get the saturation of the cells. Okay, so yeah. So sometimes, like in the transition zone, like within the contacts, you usually do your calculation of the fluid in place by using the block center. You know, in which we will be having like sometimes the structure change, and it can lead into like potential or some kind of potential error if you're doing the fluid in place calculation. That's why you have an option as well to trying to divide your cell into different levels, and in this one you will be able to have the correct contact assigned to it, which will give you a better estimates for fluid in place. So yeah, in this demo, we just wanted to show you how you can use the fine scale option if we are using the initial condition process.
Edwin,
Yeah.
sorry,
Yeah.
before you go on, just to show what I was talking about the other time. You see, when you are using this process, you can indicate whether you have GOC or not. Can you see it here? So if you believe that the reservoir is undersaturated, then you say, I don't have GOC, then you can indicate it right away here. Does that make sense now?
Yes, it's Mukazu.
Yeah,
it does make sense.
Yeah, exactly. So you can actually check or uncheck from this point, before you set up the other parameter. What this will do is the moment you check it that, oh, no GOC or something, is going to automatically disable this for you. So because here you are choosing the option that you have GOC and you want to adjust it, and that is why it's disabled. The same thing if you uncheck it, what will happen because you are saying I don't have GOC. This one you have GOC, but you are not sure exactly where it is. So you want to kind of let the simulator adjust it for you based on the RS. So there are different flexibilities here. It's just to look at this and be creative to set up your initial condition. So Edwin, please go over. I just want to use that to answer his question.
That's fine. That's fine. So as you mentioned, like with this process of initial condition, you will be able to. Okay, so with this one, you activate the levels and the tilted, and you try to classify subdividing your cells into how many levels, and this is whereby we do it through this process. And this is by using the option we selected here for the simulator is the intersect. All right, and then within the intersect itself, there is like a user keyword that we are going to use to give us the same flexibility of doing the fine scaling. So you go to for the intersect, you go to user edit and create this fine scale option through we have a keyword here called questions. And here, this is the whole process that you're doing by defining the fine scale and the other options. here we select the option of equilibration and we want to do like by using the pivot norm 1 fluid model. Okay. All right. And we choose to fine scale it into different levels. Is it the same at your side, Sam?
Yes.
Okay. And then we divide it to the different levels. This is how we create the user through the user edit in Intersect. And then if you go to define simulation,
there is lag time in the video between myself and you, but
okay,
I'm trying
but at
to
least
see.
it's clear, right?
Yeah. So I'm
I
trying
hope if
to
there's anything.
adjust it
Mm-hmm.
just so that it can help people to follow. So
Mm.
what Edwin is trying to do now is to define the subdivision for the fine scale definition that he explained in the previous slide. And that's all you need to do if you're using intersects, actually.
Yeah, so in Intersect, if you're using Intersect, then you should just add this user edit that we have done it. You add it into your Intersect tab within the defined simulation case, and then you run your case. After running the case, I will be showing you as well, like, with once you do the initialization, you should have check the stability of the initialization, right? So this is the next thing that we are going to show you in the demo. So through the multi-value prop, you drop both your simulation case and then drop both the pressure and saturation results, and you check the value at your transition zone to see the stability. So throughout all this, like 1 month of like in the field management strategy that we define, you can see the pressure is stable, and you can see the saturation is stable as well. And with that one, this is the end of the demo. All right, the other method of like initialization is through enumeration, as we mentioned before, depending on the number of the phases that you have, whereby the parameters that you should define into your simulator, okay? And in case of the black oil, then you need those at least pressure, saturations, plus your composition. And in the compositional case, you need additional like solutions of vapor and liquid components. For the thermal case, you need the initial temperature. Okay. Okay. So as you mentioned in the previously about the restart, instead of doing your simulation, if you're doing both history matching and prediction, you can create a restart case, and with the restart case, you will be able to predict and I mean, like at least refer to your restart file, whereby you will be having both the pressure and saturation of the cells consistent. With that one, I will pass it to Sam to continue with the presentation.
Okay, thank you so much, Edwin. So we're just going to continue from what Edwin has been going through. To recap what he has talked about, he has shown you 3 different methods of initializing the module. The first one is using equilibration. That means that you're providing some properties that will help you to calculate pressure and saturation prior to production commencement. The second one is the enumeration, whereby you have to provide the saturation and the pressure explicitly, because it is important for the simulator to know where you are starting from before the simulator can actually proceed to calculate the dynamic behavior of your field with time. So the last one is the restart, that is talked about, whereby you can pick the solution at a particular time instead of computing everything from the from the inception. You can actually pick the solution from somewhere and proceed from there. All these methods that you've seen, any of this simulator would take, let's say, the saturation of the water above the transition zone to be a constant value. And with that method, you're going to have something that looks like the graph that I have on my left-hand side. In the transition zone, you're going to see the variation that shows the distribution of the, let's say, water saturation. And above the transition zone, you're going to have just a constant value of the coordinates. And below the free water level, you're going to have the maximum water saturation of 1. However, there are situations whereby you might need to actually honor the observed initial water saturation distribution provided by a petrophysicist or your geomodeler. So in that case, because we know that the reality is that, Edwin, please pay attention on admitting people into the meeting. I see that people are still joining. If you look at this, you have the water saturation, but above the free water level, you still have the water saturation that is not really constant. The reason why this might happen is because of the water saturation distribution would depend on the pore throat geometry that you've got, would depend on the reservoir quality index that you have. So there are so many factors that is controlling the distribution of this water in the pores. That is why it is not usually a very constant value like we see here. So when you have the water saturation provided by your petrophysicist or your geomodeler, like I said, how do you honor this when you are setting the simulation up to ensure that the implementation is actually correct? Two common methods are the use of the J function and at the same time using the initial water saturation array by scaling the capillary pressure. I'm also going to show you another approach after these two that you can actually use depending on water saturation. Maybe you are getting it from saturation height modeling and you have the equations for the Bruce-Corey or any methods that you've used. How can you actually use this and do the implementation correctly from the simulation end? The first thing that I would like to mention to us is it is important for the simulator to ensure that we have that consistency between the saturations that you have and the pressure in the system. That means that they have to be consistent regardless of the fact that you are providing the water saturation array. Then the simulator will have to honor the water saturation and ensuring that the prevailing pressure is still consistent with the water saturation that has been provided by you as the user. So what is going to happen is it's going to scale the capillary pressure. So how does it do that? I want you to just imagine this purple curve as the capillary pressure that you have provided as inputs into your simulator. Simulator is going to calculate in every cell, let's say in a cell in the transition zone, the simulator is going to look at the pressure, the phase pressure, let's say the oil pressure, the water pressure in that cell, and is going to find the difference, which will give you the capillary pressure, and is going to go into the curve that you have provided, and is going to check what the water saturation should have been in principle. The water saturation should be SW based on the curve that you have provided. However, you are now providing another water saturation for each cell, which is SWI. And the SWI is now different from what the saturation should have been if the method that used the equilibration approach that we already explained to you previously. So what the simulator is going to do in that case is to scale this capillary pressure, the purple one, down to the yellow so that it will make the capillary pressure that you have to honor the water saturation that you are just providing now. And that is how it works. That means that what the simulator does is whenever you provide the water saturation array, the simulator will ensure that this water saturation array is honored by scaling the capillary pressure down to the value that will give you. One thing that I want you to pay attention to while you are looking at this is the fact that the scaling of the capillary pressure will be vertical scaling. It will not do horizontal scaling, because doing horizontal scaling will change the initial, because that will affect the coordinate water saturation value, and that will affect, in fact, your calculation of the fluid in place. So it doesn't do that. Instead, it will do the vertical scaling in order to match the water saturation that you are providing. So one way to do that, like I said, is to use the J function. Actually, the J function, leverage J function approach, which will relate the permeability, the porosity, the capillary pressure, interfacial tension. All these parameters are actually inherent in this dimensionless function. It's using that to scale your capillary pressure that you are providing and scale that capillary pressure to a J function using these parameters. What is the benefit of actually doing that? You see, whenever you are using the dimensionless group like that to normalize maybe a variable like capillary pressure, and that will actually remove the variation that you are having in your data. You have to bear in mind that when you are doing this, it has to be performed on rock type basis, right? The relationship applies as long as you have similar pore geometry, that is similar rock type. So what happens when you try to do this is what you are seeing here. After normalization of the PC by the J function, which is here on the left-hand side, I've got the PC curve for sand A, sand B, maybe taken at those locations. But by the time we try to normalize it and change it to J function, then everything will come close together, as you can see here. So what we're trying to do is, instead of trying to provide capillary pressure curve for each cell in your module, because they have different porosity, different permeability, if you can actually normalize the available capillary pressure that you have to J function, you can now provide the J function to the simulator. Then the simulator will use the porosity, permeability, water saturation, and so on and so forth to scale that leverage J function to give you the individual capillary pressure per cell. So what is going to happen now, you have capillary pressure per cell in your module that is consistent with your water saturation that you are providing. And of course, this can also be obtained from your petrophysicist directly. When it comes to the implementation, it's not actually as difficult as you look at it. Because what you are doing here is, you go to the either eclipse, intercepts, and you have to provide J function. That means that you must have normalized the capillary pressure that you have to give you the J function. What is important in this normalization is make sure that whatever you're using for the interfacial tension and water, maybe from petrophysicists, you can also get this curve from them. So tell them to normalize because in TechLog, we can do that. I can show how to do that. So if you get the curve directly or the table from TechLog, and that is the benefit of actually the integration that we started last week. If you can get that, then that will really improve the credibility of what you are doing here. So the same sigma and theta that you use, just provide them also to the keyword that requires that in Eclipse. That's the JFunc keyword. If you are using Eclipse and Intercept 2, you have the node that you need to provide that. Once you provide that, it's going to normalize, it's going to take your J function back to capillary pressure. So this is what it's going to do. So for every cell, on the basis of the variation in their porosity permeability, it's going to give you the capillary pressure back. And that will really bring the heterogeneity that you expect with respect to capillary pressure to every cell in your module. And that is the beauty of using the J function. The second method to honor the water saturation array is to use what we call matching the initial water saturation distribution. In Eclipse, they call it sorting it. In Intercept, you can just say you are matching because Intercept is not using keyword. But if you're using Petre to set it up, it is very easy to implement. Let's forget a little bit about the theory of scaling capillary pressure and everything. Implementation is really easy. Let's say I've been provided with water saturation array property in my Petre project. All I need to do is to drop it here and make sure that I select the right template. The template that you will require to do this is water saturation PC scaling, SWOT in it. Make sure, as long as you take this, what you are telling the tool to do is to scale to honor the water saturation array that has been provided here while scaling the capillary pressure. And it will use the method that I already explained about scaling the capillary pressure to ensure that the prevailing pressure in the cells are actually consistent with the saturation as expected right from the beginning. But with this method, you have to provide PC curve. That means that you also have to provide the corresponding PC curve. What is interesting here is sometimes we don't know that the petrophysicists can actually give us that PC curve. Because if they have calculated the SWOT in it, the water saturation, let's say based on the SHM module, then you can actually ask them to provide you an equivalent capillary pressure on the basis of the rock types that they've used. And if they have that, you have to supply that to the simulator. That capillary pressure will now be scaled per each cell to ensure that consistency that we've been talking about. That is one way to do that. After running the initialization, you can actually use the simulation table probe to check whether those capillary pressure are actually scaled, particularly along the transition zone between the phases changes. So in this case, if you click on any cell here, you will see the unscaled, which is the yellow one, and the scaled one. So you will see that your capillary pressure has changed, but at the same time, you are now able to honor the saturation array instead of having something constant. Sometimes the capillary pressure may not scale in some cells, particularly if your PC equals to 0. That means that maybe in the water zone, because water saturation is 1 and oil saturation is 0, so your PC is there is no PC there. In that case, you don't get a scale. Another time that you don't get a scale is if your irreducible water saturation, or if you want say coordinate water saturation, if it is greater than the saturation in any particular cell, then for that cell, the capillary pressure will not be scaled. The last one is the PC curve. If you don't provide the PC curve, then you don't expect any scaling anyway. So I'm going to demo that to you just to see how to implement that. Then I'll take you to the last part, whereby we can link it up with what we actually did last week. What you're looking at here now, I've been provided by my geomodeler the water saturation that you are seeing here. So I'm going to open my case. Instead of doing the equilibration on the basis of the endpoint, I'm now going to try to honor my water saturation array that has been provided by my petrophysicist. So I'm going to name the case. I'm just opening a case. This is a normal case. If you use this case, it will run, but this case is using the direct equilibration approach. If I'm going to honor the water saturation, then I take that water saturation property and append it to my grid section. Make sure this is the main thing that you need to do. You are changing the water saturation scale template to water saturation PC scaling. Once you do that, that's all. You don't actually have to do any other thing again. You can just go ahead and run your simulation. I mean, here it's initialization, so I don't need a strategy for now. I just want to initialize the module. So just run it and see the outcome of initialization. And that is how easy, how straightforward it is when you are trying to honor the water saturation array using the initial water SWOT in it, actually, whether you are using Eclipse or you are using Intercept. It's the same way as long as you're using Petre to set it up. In a few moments, the simulation will finish. Then we can just look at the results. Just so, I mean, it's completed. I can see now 100% complete. So what we're going to do now, let's look at the results. This is the initial water saturation provided by the petrophysicist. Now I'm switching to the new case that we've run, and I'm going to check the water saturation that's provided. One thing that you can also do is let's display that water saturation. It's pretty the same, qualitatively. If you want to make the analysis more quantitative, you can use the function window to do a cross plot of the previous one provided and this. It will line up on your cross validation plots to show that they're actually the same. Once that is done, I also want to show you to see that some pressure, capillary pressure, they've already been scaled. Let's click on that cell. You can now see the unscaled one in yellow and the scaled one now in green. So that shows that we honor the water saturation in those cells, but we also scale the capillary pressure. Let's move on to the last part. You can now check all your results if you want, check your in place, and many other things. So I'll leave that for you. You can undo that already. So last week we started how to actually create water saturation array, and we tried to link that up with generation of your table for your model initialization or for your dynamic simulation. So I'm just going to take a quick recap on that. Then I will link that up with the story of initialization, and that will bring us to the end of this section. The way the petrophysicists, the way they actually model the water saturation is to make sure that this water saturation, you can see if I'm using Brooks-Curry correlation, there are many correlations like I showed you last week, but this one is particularly Brooks-Curry, and he's saying that the water saturation is equals to the SW, the irreducible water saturation, but actually this value here is the irreducible water saturation that corresponds to the model. So it is not purely the true irreducible saturation in the reservoir. It's just mathematical. It's representing the point where you actually have the asymptotic behavior. That is where the irrespective of the value of your capillary pressure, that value of saturation will be constant all the way through. And that is this value from the Brooks-Curry. But that might not actually be the true irreducible water saturation in our model, because our model is limited by the height of the reservoir. And it might not just be. If you look at this example, is this red line and this green line. In the lab, they could measure capillary pressure to show the entire pore geometry of your core sample. But in your reservoir, the height of your reservoir will limit your capillary pressure, and the capillary pressure limit will also change the irreducible. And that is why this is a very strong integration. This decision of this height should be taken by not only petrophysicists, it should be taken by geomodeler, and as well as getting input from reservoir engineer, because this actually will impact, when we build the water saturation, will significantly impact what your irreducible water saturation will actually be. But you see, this one is representing the value here that goes to infinity. It's asymptotic according to this formula, but I may not go so much into the theory behind it, but that is the reality. But let's look at the water saturation, that it depends on the irreducible water saturation plus 1 minus irreducible water saturation multiplied by the entry pressure divided by the PC, all raised into power inverse of n. N is the pore size distribution parameter. We have 3 important parameters here that water saturation depends on. It depends on the irreducible water saturation, it depends on the entry pressure, and it depends on the N, the pore size distribution parameters. Each of these also depends on the reservoir quality, like the porosity, the permeability. Now you can see how they are dependent. So what we do when we try to model the water saturation is the petrophysicists will try to create model capillary pressure curve based on the petrophysical properties such as porosity and permeability. They will model, that is the red one. They will try to model the capillary pressure. And that capillary pressure that you've modeled, you will now relate it to your water saturation. And that is how you are able to calculate the water saturation. So you first of all model the capillary pressure, And when you model the capillary pressure, you have to, as you can see, that this water saturation depends on all these parameters. So they play around with all these parameters in order for them to get the water saturation out. But once you have the water saturation ready for you, then you are kind of in a good shape to move on. And they can also, and that was why I was telling you that they can provide you the capillary pressure curve, depending on the method that they've used. There are so many methods that can be used to generate the water saturation array from the petrophysical end. One of them, is the one I just showed you in the previous slide, which is the Brooks scoring. We also have FOMIA, we have lambda, we have J function. All these depending on the source. So reservoir engineers should be conversant with the source of the water saturation to really understand where is the water saturation coming from. Then that will help you, because they might be able to help you with maybe J function table or PC table that you will need for the initialization of the module. Another workflow that I've not talked about that people use a lot is now this that I want to take time to explain to you. And this will now take me to the last slide where I really show you the big picture of the workflow that we do when we do initialization, particularly with this method. Then I will give room for question and answer. Again, just to recap what we've been talking about, you have water saturation array from your petrophysicist or your geomolar. You can either, depending on the source, if it is coming from J function, you can get the J function and use the J function approach. You can also use the capillary scaling approach, scaling it to honor the initial water saturation that you've got. Another approach is what I'm about to explain to you now. So imagine that you have the SHM module from your geomolar, that is the saturation height modeling. Don't forget that I mentioned that those parameters, the 3 parameters that water saturation would depend on, actually the 4 parameters. The first one is the SW INF. Why I call it INF is actually this is the one that goes to infinity on the basis of the equation. It's not truly the irreducible water saturation, but that is okay. We need this parameter to adjust the curve to get the water saturation. We also need the entry pressure, and you can see in this case it depends on the permeability. Sometimes it could depend on porosity or both of them. But in this particular example, this SWINF depends on the permeability, PCE depends on the permeability, and the N, which is the pore size distribution parameter, is given as a constant. You can calculate the capillary pressure. This is easy. Pressure is just H rho G. So if you're finding capillary pressure, is the pressure difference. And that is why we have density difference, the rho. H is the height above free water level, because that is when we begin to have the capillary effects. Then this is your G, and this is actually to convert it to the reservoir condition, because here you are having 1 over interfacial tension cos theta. Your cos theta is 0.866 in this. So this gives you capillary pressure. And this, if you put all these parameters in here, you can get water saturation. And this is what has been done in a nutshell from the SHM by your petrophysicist. What you are going to do now is to take the same function that they've used and reverse the same function. And Techlog can do this for you automatically. And that was one of the workflows that I discussed last week. So you can just do it. You don't have to do it manually, but look at it. You get your SWINF, which is the first one. Sorry about that. You get your PC entry pressure using the same equation, and you get your N. It's the same value, so you use the same thing. That means that once you have that, the next thing that you're going to do, express every other thing in this equation as capillary pressure. So making capillary pressure the subject of the formula here. So you're going to get this expression. Notice that I've changed the SWINF, which is the asymptotic irreducible water saturation. I've changed it to actual irreducible water saturation here, because the capillary pressure that you are getting, the model capillary pressure that you are getting, must have been capped to represent the height of your reservoir, thereby giving you the true or a representative irreducible water saturation in your module. And that is what you have here. So I have SWIR here. Now, in order to calculate your capillary pressure, imagine if you provide saturation, just provide the range of saturation, which is SW, and you know your irreducible water saturation. Then you can calculate, because N is known, PC is known. That means that you can calculate capillary pressure column automatically. And that is why you can get it directly from TechLog, because everything is sitting in there. The next thing that you want to do is to calculate your relative permeability. You can use LET or you can use Corey. This is an example of using the Corey correlation for the water. We have for the oil too. We have for two-phase system. So in the oil water system, this is the water. So the water will be the relative permeability of water at the residual oil saturation multiplied by the normalized saturation, raised into power the Corey exponent for water, which defines the shape of your relative permeability curve, basically. So that means that you need to know this important. There are a few important parameters here. You need to provide this, which is this one. I'm talking about KRWO, which is the relative permeability of water at residual oil saturation, which is this. You need to know the residual oil saturation, and perhaps they are very important in this equation, as you can see. Of course, you need to provide your exponent as well. With that, you can generate the table for KRW and KRO. And this is how you will form your table back from your saturation height modeling equation that has been given to you. And the moment you make this table back, but again, like I said, it can actually be, you can generate it automatically from TechLog. That was one of the workflows that I was showing you last time. So once you have this table, you can initialize your module. But another step forward is you don't want to use a single table to initialize the whole module. Bear in mind that this is for a single permeability. So if you are doing it for a single permeability, let's say you now take average permeability for your whole reservoir, you might not be able to match your stoil if you use this approach. So what people do is to create permeability bin. That is, you're going to subdivide your permeability into small fraction and create the table for each permeability bin and use that to initialize the module. And if you use that to initialize the module, your workflow will look like this, which is going to be the last slide for this presentation. Then I will open room for question and answer. Okay, in this workflow now, you can now create permeability bin and say, okay, between this range 0.01 to 1, it will be a bin. From anything between 1 and 100 millidarcy or 40 millidarcy will be between this. So you create the brain, then you try to initialize the module. Once you run the simulation module, compare your static and dynamic result now that you are getting together to get tolerance less than 1% at the field level, at the reservoir level, at the phase shield level, whatever the situation may be. You check, you will see that at every level, you will have very, very minimal difference between the stoil that you have by the geomodeler and the one you have in the dynamic module when you follow this approach. If your value, the difference is more than this 1% tolerance, some companies will say 5%, but 5%, it depends on the size of the oil that you are talking about here. In a big field, 5% could be very significant. Again, even 1%. Whatever tolerance, that's another topic that you are choosing. If you are not meeting that, then you have to adjust your bin size. Then that is, you increase the number of bins by reducing the spaces. That means that if you have taken between 100 millidarcy to 1000 millidarcy, you can now split it to 100 to 500, 500 to 1000, just to increase the bin again. and you recreate the relative permeability for each bin, and you launch it again. And when you create the relative permeability, you have to create the SAT-norm property for each bin. So the SAT-norm will correspond to each bin. Then you run it again and compare the result until your result is now below the tolerance. Then you can accept the initialization results. And that is another way to take advantage of this. So in summary, we have shown you the different methods of initializing models using our simulators, Eclipse, Intercept. We've shown you how to control initialization options as well, particularly in Intercept. I tried to explain the concept of capillary pressure scaling and also how to match your initial water saturation. Then I also presented a workflow whereby you can actually take advantage of the information that you have in TechLog that was used to build your saturation height modeling and use that to initialize the model on the basis of the bin definition that you are defining. And that brings me to the end of this section. I'm happy to take your question now. Just feel free to unmute yourself.
Yes. Yes, I just want to go back a little bit in the very beginning of the initialization process. So when I'm defining the properties of my of the fluid that I have, for example, let's say I'm only obviously defining for a single rock type, and then I put the properties of that fluid, and I insert a certain table for that fluid as well, right?
Yeah.
Yeah, on the fluid model. But we've seen that, I've seen that even on the fluid model, I still have the option to put some values for initial conditions there.
Yeah.
I wish I could actually be able to see that, but yes, but then after that, we have the other tab in terms of workflow on the side of array. We see also another tab when it asks again for initial conditions, in which, for example, where you actually mentioned that we could either choose an option in which we have the GOC or not. So my question is, since we already in the initial tab of making a fluid model, we already stated the inputs for the initial conditions. No, we don't need again to go into the initial conditions tabs and input those values, since we have done that in the fluid model by introducing a PVT table in there.
Yeah. Okay, thank you so much. The two processes are different. That was why Edwin said at the beginning, maybe you missed that you can either use make fluid module to do it, or you can use the initial condition process. If you are using make fluid module, you've already specified your contact, all those information. So you don't have to come back to initial condition process to do it again. These are two different processes doing similar stuff. The only thing is the initial condition process is actually designed for intercept, while the make fluid module process was designed for Eclipse originally. But you can use the initial condition process for either Eclipse or Intercept. But you are not supposed to use both of them. So once you have specified, your observation is correct. So you have to stick to one. Does that make sense to you?
Okay.
There are
yes,
two
it does,
different processes. Yeah.
Okay, so I have another question when we come to defining the simulation. I just don't know if I put myself ahead of someone.
Yeah, I said that.
Can I go ahead asking?
Antonio, I will come to you in a moment. Yes, you can go ahead. Yeah, go ahead and finish.
In the define
somebody else. Yeah. Okay. Go ahead.
Yeah. So in the defined simulation case, when we actually selecting all the grids, if we don't have, let's say, the SWOT in it, if we don't have that, we didn't get that from from the geological model. Is there another way that we could go about and then set the connect water saturation plus the critical water saturation to be able to run the model? Will that also give us, in terms of initial STOIB to compare with the static, will it give us a solid value by not having the SWOT init template there and its property there properly defined? I don't know if I'm making sense. I'm saying if we don't have the SWOT in the initial saturations, for example, the properties to add in this grid, but we have the connect water saturation and the critical water saturation. So will this two be okay to be used, or I mean, in terms of getting results, how far off will our results be? That's what I want to understand.
So there are two ways to look at the problem, right? If you don't have the initial water saturation array, the simulator will use the equilibration method that my colleague explained previously. So what is happening is, let's say there is no transition zone. What the simulator will do to know the saturation in each cell is to look at your relative permeability curve that you have provided. This is for the oil and the water relative permeability curve. And look at what is the saturation on this relative permeability curve, the coordinate saturation that you have here. So it's going to look at every cell below the oil water contact. Since there is no transition zone, it's going to assume that the water saturation here is equals to 1, and the oil saturation here is equals to 0, and the gas saturation here is equals to 0 for all the cells below the oil water contact. Now, going to above the oil water contact, since there is no transition zone, the simulator is going to say your water saturation here is equals to the coordinate that you've got on your table here that you have provided. Let's say it's 2.2 or thereabouts. What the simulator is going to do is to say SO will be 1 minus SW, which will give you 0.8, and SG will be 0 here. And if you go above the GOC, again, the coordinate water is 0.2, but the gas saturation will be 0.8, and the oil saturation will be 0. Now, the simulator knows all the saturation values in all your cells. However, if there is transition zone around the contact, let's say this is the transition, it's going to go below the free water level and say saturation here is 1. And again, for water, for oil is 0 and gas is 0. It's going to go above the transition zone. Let's say this is the transition zone, TZ. It's going to initialize this using this method. But for this transition zone, my colleague explained to you that it's going to look at your capillary pressure, calculate in every cell what is the oil pressure, what is the water pressure. Based on the oil pressure and the water pressure, it will do a lookup and know what the saturation value will be for water. And once you know water, you know oil, you know gas. So it doesn't matter, you don't have to provide the water saturation array. It's just another way. We're just explaining different possibilities. And now you need to answer scenario that you encounter. Have I answered your question, Mukazo?
Yes. Thank you.
So, Antonio, I saw that you raised your hands before. Do you still have the question?
Yeah, I still have the question. First of all, good afternoon to all. And
Good
I would
afternoon.
like to thank you for the great presentation. It was clear to understand what is modern initialization on all the method that we have. So my question is more so related with reservoir quality versus capillary pressure. Let me put it this way. For example, when we have a very good sand, a clean sand, normally on those cases, most of the time the transition zone is almost 0. And for low permeability or tight rock is where we most of the time we use the capillary pressure. So my question is, normally when we have a very good sand, we don't use the J function or capillary pressure because we know that the transition zone is not that very important. Just to make the workflow very simple, we only have the tendency of using the capillary pressure when we know that we have a very big a very important transition zone. I don't know, what is your comment on that kind of approach?
So thank you so much. I guess that's a very good one. We all know how difficult sometimes it is to have capillary pressure data, but it's actually a very good assumption. If you have a good sand or reservoir, based on the reservoir quality, then what you are getting is something close to this K1 plots, right? Showing that there is almost no transition zone in my reservoir. And in that case, it's going to use the relative permeability water saturation, the coordinate, to define the water saturation in this region. And that is actually when you use the first approach that I explained to you here. That is what you are doing here. So it's just taking the water saturation that you have here and use that to say above the oil water contact, your coordinate water is 0.2, then oil saturation is 1. For gas, above the gas oil contact, your water saturation will be 0.2, gas will be 0.8, and water will be 1 below. Very simple. That is based on the assumption that the rock is very good quality and the transition effect is really minimal. Okay. Another thing is, if you have very tight formation, which is K2 now, transition becomes really significant because even your entire reservoir may fall in the transition zone. And in that case, modeling the transition effect will be priority. Otherwise, you might be overestimating the oil saturation and underestimating the water saturation in your model. That is one scenario. Another scenario is if you have heavy oil. For heavy oil system, where the difference between the oil and the, I mean, if you see, I guess I have something like that I didn't mention. Look at this. If you have very small difference between the density, because capillary pressure depends on the density. If you have a very small difference, that means that you are dealing with heavy oil whose density is as close as possible to water. Then in that case, transition effect will become significant again. Unlike when you have a large density difference between the fluid, maybe then the transition effect will become really insignificant. So it depends. It could be driven by the rock quality. It could be driven by the fluid properties, the need for transition modeling.
Okay, thank you very much. I got your point.
Yeah, you're welcome. Okay, if there is no other question at this point, okay. Mr. Sam, yeah, I can see.
Good afternoon,
go ahead.
Sam.
Go ahead. Good afternoon, sir.
Yeah, thank you for the presentation. I just wanted to know on the generation of the saturation table that you mentioned, does it help in any way in the history match, or you just to get the initialization and probably get your endpoints?
Very good question. So definitely what happens subsequently depends on what you have initialized. That's number one. Plus, because all the calculation now will build on that and move on from there. So if it is wrong from there, then obviously something is wrong from the start. That is the first comment that I will give as a feedback. The second comment that I'm going to put is, all the mobility calculation, all the calculation is now done using the curve that you have. That means that if you don't pay attention to this, again, that will really impact your history matching, because the mobility calculation is completely different from the actual mobility in your reservoir. The mobility from your simulator based on the data you have provided is different. So that could become significant. Having said that, we all know that one of the most uncertain parameters in our simulation is the saturation function. so uncertain, even though when we think we pay so much attention to modeling it, because it's a lot of uncertainties. But we can't rule out the fact that if you try to pay attention to modeling it, at least reasonably and more representative of what you have in the reservoir, then of course you are minimizing the disparity that will bring into your result later on. Again, it has impacts, I would say. That would be the answer that I will give to your question. So doing it right from the beginning helps a lot.
Okay, thank you.
You're welcome, sir. Okay, I believe that we've stretched the time a little bit today because we've tried to reset the time back to 1 hour just to make sure that we accommodate all this busy schedule. So we want to say thank you so much for your time today. We also look forward to see you next week. And next week, we are going to start a very interesting topic. Let me just zoom out, I guess. I can do that. So we're going to have a very interesting topic next week. That is on sensitivity analysis, uncertainty analysis, and proxy, okay? That will be taught by my colleague, Enio and Carlos. Then the week after, we move on to talking about optimization, history matching, and that will also be taught by Limi and myself. We'll finish this round of topics. Then we'll come up with a new set of topics again to continue to support you. Thank you so much once again for your time, and see you next week.
Thank you.
Okay.
Thank you.
Bye-bye. Thank you very much.
Yeah.